Hello everyone, welcome to tutorial number 5. So let's start with question number 1. We have to show in question number 1 that these two sets have the same cardinality. So the first set here is the set of all real numbers between 0 and 1, but excluding 0 as well as 1. Okay. Whereas the second collection here, it's also the set of all real numbers between 0 and 1, but 1 is inclusive. That means 1 is allowed. That's why the square bracket here, and 0 is not allowed. Okay. So that's the interpretation of these two sets. We have to prove that these two sets have the same cardinality. How we can do that? So recall the Schroeder-Bernstein theorem, which says that if you want to prove that two sets have same cardinality, show injective mappings from the first set to the second and from the second set to the first. Okay, so we are going to do the same thing here. So here are our two sets. Let's consider the injective mapping F, which is the identity mapping. Okay, so clearly this mapping is an injective mapping from this set to this set, because you take any two different real numbers x and y, the corresponding images will be x and y, and they will be different, and they will be in the range. They will be in the range which is the valid, which is allowed as per the function f, right? So your domain is not allowed to have the numbers 0 and 1, and so is the images. Okay. Now, if I want to take the injective mapping in the reverse direction, then consider the injective mapping G defined to be x over 2. That means if you want to find out the value of g of x, the output is x over 2. So that means if your x here, which you are considering, is different from 1, then clearly that will fall in the range 0, 1. Okay, and excluding 0 and 1. But if your x is equal to 1 as well, then the image of 1 will be 0.5, which is well within the allowed limit here. And it's again easy to verify that your mapping G is an injective mapping, right? So since we have shown here two injective mappings, we can conclude that the cardinality of these two sets are the same. Okay, in question number 2, we have to prove that there is no infinite set A whose cardinality is strictly less than Aleph null. Okay, that means whose cardinality is strictly less than the cardinality of set of positive integers. So in some sense, we want to prove here that Aleph null is the smallest infinity here. Okay, so to prove this statement, we will use two claims, and we will assume for the moment that these two claims are correct, and later on we will focus our attention on proving these two claims. The first claim is that if you have any set A whose cardinality is less than equal to the cardinality of set of positive integers, then you can always find a subset of the set of positive integers which has the same cardinality as your set A. Okay. So pictorially, what I am saying here is that you may have a set A whose cardinality is less than equal to the cardinality of this set Z plus. What I am saying here is that in this claim, the claim says that you can always find a subset B within the set Z plus whose size is exactly the same as the size of A. And claim 2 is that any subset of the set of positive integers is either finite or has the same cardinality as Aleph null. You can't have any other third category of subset of the set of positive integers. So for the moment, assume that these two claims are true. Okay, let's come back and prove the statement that we are interested to prove. And the proof will be by contradiction. So we want to prove that there is no infinite set A satisfying this condition. So we will assume that on contrary, suppose you have an infinite set A whose cardinality is strictly less than Aleph null. Okay. Now, by applying claim 1 on that set A, we also know that there exists some subset B of the set of positive integers whose cardinality is same as the cardinality of your A set. And now if I apply the claim 2 on that subset B, I know that the subset B has to be countably infinite, because the subset B is a subset of the set of positive integers and it will be either finite or countably infinite. So B is definitely not finite because the cardinality of B is same as the cardinality of A, and we are assuming here that A is an infinite set. So we are left with the second category here. That means the cardinality of the set B is countably infinite. But we also know that the cardinality of B is same as cardinality of A. That means the cardinality of A is also Aleph null, because B is countably infinite. So the cardinality of B is Aleph null. That means the cardinality of A is also Aleph null, which is a contradiction. Right? So now the proof boils down. How exactly we prove these two claims? They are very simple. So let's first prove claim number 1. So since the cardinality of A here is less than equal to the cardinality of Z plus, then as per the definition of cardinalities, we know that there exists an injective mapping from the set A to the set of positive integers. Then only the cardinality of A can be less than equal to the cardinality of Z plus. So based on that injective mapping F, I am going to show you the existence of the required set B. What do I do basically is I just focus on the range of the function. That means I pick up the set of images of this function F. That means all the valid images as per this function F. And since my function F is an injective mapping, each element of A will have a unique image. So how many images I will pick? I will pick the same number of images as I have the number of elements in the domain. That means the range set of F, namely the set B, will have the same cardinality as the cardinality of your A set, right? So that's a very simple proof for claim number 1. For claim number 2, we have to prove any subset of Z plus is either finite or countably infinite. So if we pick a finite subset of Z plus, then the proof is trivial. So let's focus on the case when we have chosen an infinite subset of Z plus. Okay. Then the idea here is that we know that Z plus is countably infinite, right? That means it's possible to list down the elements of Z plus. And B is a subset of Z plus. That means what I can do is I can always say that it is possible to list down the elements of the B. Why? You just list down the elements of B in sorted order. That's all. Because B is a subset of Z plus and it's always possible to list down all the elements of Z plus. So depending upon which elements are there in B or which elements are not there in B, in the sequencing of Z plus can remove first all the elements which are not there in B. And if you arrange all those remaining elements in a sorted order, then that gives you a valid listing of the elements of the set B. And if we have a valid listing of the elements of an infinite set, then that's a countably infinite set. So that shows that your subset B is countably infinite, which proves your claim number 2. In question number 3, you are asked to show that if you are given an infinite set, then it doesn't matter whether A is countable or uncountable, you can always find a subset of A which is countably infinite. Okay. So of course, if my set A itself is countably infinite, then the subset would be the set itself. But in the statement, I am asking you to prove this even if the set A is uncountable. So even if my set A is the set of real numbers, which is an infinite set and not countable, I am asking you to prove the existence of a subset of real numbers which is countable and infinite. Right? So we will prove this general statement. How we are going to prove this? So since A is an infinite set, it will have at least one element. Arbitrarily I pick that element. I call it as A1. Now my claim is that if I remove that element A1 from the set A, the remaining set is still an infinite set. Why? Because if this remaining set A minus A1, if this is finite and if its cardinality is say M, then what can I say about the cardinality of A? I can say the cardinality of A is M plus 1, which is a finite quantity. But that goes against my assumption that A is an infinite set. So that means if I remove the element A1 from the set A, I am still left with an infinite set. Now I again apply the same argument. I focus on the leftover set, namely the set which I obtained by removing element A1, and my claim is that since it is an infinite set, it will have at least one element, A2. I pick it arbitrarily, and my claim is that if I now remove the element A2 also, I have already removed A1 from A, and now what I am saying is even if I now remove A2, the leftover set will be an infinite set. Again, the proof follows using similar argument, because if this leftover set is not infinite, suppose its cardinality is a finite number, say n, then what I can say about the cardinality of A? I can say the cardinality of A will be n plus 2, which is a natural number, a positive number, and which goes against the assumption that A is an infinite set. Okay. So I can keep on running this argument, right? And what I can say now is that in each step, in each iteration, the arbitrary element which I am picking, right, from the leftover set, if I list it out, if I list down all those elements, then that sequence of elements will be, or the set of those elements which I am picking in each iteration from the leftover set will of course be a subset of my original set, because in each iteration I am picking an element from the leftover set, and each iteration the leftover set is a subset of the original set. And what I can say about the set of numbers which I am removing from each iteration, I can say that its cardinality is Aleph null, because I now have a valid sequencing for the elements in that subset. Namely, I can arrange the elements in that set T in the order in which I have removed those elements in each iterations. Okay, so that shows that I can always find out an infinite subset from in the set A whose cardinality is Aleph null. Okay. In question number 4, we want to show that if I take several countable sets and take their union, namely if I perform union of countable number of countable sets, then the resultant set is again countable. So imagine you are given several countable sets, namely you might be given infinite number of countable sets, and without loss of generality let they be disjoint. So I call the bigger set S to be the union of all these sets Si, and I want to show that this bigger set S is also countable if each of these individual sets were countable. So what we have to do basically is we have to show how to list down the elements of this bigger set S. So since each of the sets S1 to Sn and Si, each of the sets Si is countable, it will have a listing of its own, right? So imagine that the listing of the elements of the set Si is this. Okay, it's an infinite list, and the guarantee is that each element of the set Si will eventually occur somewhere. So I have written down the listing of all the elements of various sets here. So this is the listing of S1, this is the listing of S2, this is the listing of Si, and so on. Now based on all these listings, I have to come up with a listing of all the elements in the set S, so that I will not be missing any element, and we will never get stuck infinitely while finding any element in the resultant listing. So here is the way we can list down the elements of the set S. So if you see here, within each set Si, I have used two indices to denote an element in the listing, right? The first index denotes the subset number or the set number that I am focusing right now. So if it is I, then the first index will be I, and the second index basically denotes the position of the element, whether it's the first element or the second element or the nth element, and so on. So what I am going to do is, when I want to list down the elements of the set S, I will list down according to the pair of indices I, j, and I will start by listing down all the elements of the form Sij such that the summation of the two indices is 2. Remember, the minimum value of the summation of the two indices will be 2, because I can't have an I comma j such that I plus j is 1. For that to happen, at least one of the I or j has to be 0, but I don't have any index taking the value 0 here. So the least value of the summation of the two indices can be 2 only. So I will be first listing down all the elements where the summation of the indices will be 2, followed by listing down all the elements whose summation of indices will be 3, and so on. Now, when I am listing down all the elements whose summation of indices is n, then you can have several numbers of that form whose summation of indices is n. So, within that collection, I will be following a sorted order. That means I will first write down according to the index I and then according to the index j. So to demonstrate here, if I focus on all indices, all pair of indices ij whose summation is 2, then I have only one entry, namely s of 1 comma 1. Next, I will focus on all sij's where the summation of I and j is 3. So I have s of 1 2 and s of 2 1, and you can see that I am listing s of 1 2 first and then s of 2 1, because I gets preference first. So I will list down all the Sij's where I is equal to 1, and then followed by all Sij's where j is bigger than I or 2. Okay, sorry. So I will first, so I have two elements here. I have S12 and S21 to list down. So I will give preference to lower value of I first. Okay. So that's why I have written down S12 first, and then I have written down S21. Then I will focus on all Sij's where the summation of I and j will be 4, and so on. So now you can see that this is a valid listing of the elements of the bigger set S. You will never miss any element, and you will not get stuck forever to find out an element in this listing, because you take any element S belonging to the, or any element small x belonging to the bigger set S, x will belong to some Si. You don't know which set it belongs to. That means x will be of the form Sij for some j, and I plus j will take some value in the set of positive integers, call it n. So when you are listing down all Sij's such that the summation of I and j is n, you will be listing down the element x. Okay, that's why this is a valid listing of the elements of the set S. In question number 5, you are asked to give examples of uncountable sets A and B satisfying certain conditions. So we want to find out uncountable sets such that their intersection is finite. Okay, so there can be several examples. Let us take these two sets. The set A is the set of all real numbers between 0 and 1, including 0 and 1. And the set B is the set of all real numbers between 1 and 2, including 1 and 2. So remember, we proved that a set of all real numbers between 0 and 1, its cardinality is not Aleph null. So it's an uncountable set. We can follow the same argument to even prove that a set of all real numbers between 1 and 2 is also uncountable. So I'm not going into the proof of that. I leave it as an exercise for you. Now, what can you say about the intersection of this A set and B set? Well, there is only one element which is there in the intersection of these two sets, namely the number 1. And this is a singleton set, and hence it's a finite set. We now want to find out examples of two uncountable sets such that their intersection is countably infinite. Right? So what we can say here is, let's take the set A, which is the union of the set of integers along with the set of all real numbers between 0 and 1. Okay, and we can prove that this set is countably infinite. Okay, and in the same way, I take the set B to be the set of all integers along with all real numbers in the range 2 and 3, including 2 and 3 also. And we can prove that both these two sets are countably infinite. Okay, their cardinalities are Aleph null. We can prove that. But sorry, their cardinalities are not Aleph null. Sorry for my bad. A is not countable. Its cardinality is not Aleph null, even though Z is part of that. So Z is countable, but the set of all real numbers between 0 and 1, including 0 and 1, is not countable. So that's why the overall set A becomes uncountable, and similarly the overall set B also becomes uncountable. Now what can you say about their intersection? Their intersection is nothing but a set of all integers, and we know that a set of integers is countable because its cardinality is Aleph null. In part C, you are supposed to give uncountable sets A and B whose intersection is also uncountable. And a very simple example could be, take the set A and B to be an uncountable set and the same uncountable set. So if I take the set A to be the set of real numbers and the set B also to be the set of real numbers, both of them are uncountable, and clearly A intersection B will be set A itself, which is the set of real numbers and which is also uncountable. So what this equation demonstrates is that you can have various properties among two uncountable sets. You can't say anything with guarantee regarding the union and intersection. Their intersection may be finite, it may be uncountable, it might be countably infinite, and so on. In question 6, part A, we want to find out whether the set of integers divisible by 5 but not by 7 is countable or not. Okay, so first of all, what exactly is this set? So let me denote this set by S. So the set S will have the number 0, it will have plus 5, minus 5, it will have plus 10, minus 10, and so on. It won't have 35, it won't have plus 35, it won't have minus 35, because 35 is divisible by 5, fine, but it's also divisible by 7. So we are not supposed to include multiples of 7. Okay, yeah. But we are not supposed to include multiples of both 5 and 7 here. So now we want to show whether the set S is countable or not. So definitely S is an infinite set, but the question is, can we enumerate the elements of the set S? And it's easy to see that we can always list down the elements of the set according to their absolute values. Okay, and if I focus on the absolute values, then both plus x and minus x will take the same absolute value x. So what I will do is, in the listing I will write down plus x and minus x. So basically what I am saying is that my listing here is 0 followed by plus 5 followed by minus 5, then plus 10 followed by minus 10, and so on. You can't do the following. You can't say that, okay, first list down all the positive things, okay, up to infinity, and then followed by the minus things. Okay, this is not a valid listing, because if we do this, then we don't know whether we will come back ever and start listing down the negative numbers here, because when we start going towards the positive multiples of 5 in infinity, we will never stop and there is no coming back. Okay, so that's why it's only the first listing which is a valid listing, not the second one. Part B, we want to find out whether the set of all real numbers whose decimal representation consists of only ones is countable or not. Okay, so remember, the set of real numbers is uncountable, we proved that. But here we are not focusing on the set of all real numbers, we are focusing only on the real numbers whose decimal representation have only ones. Okay, no other digit. And it turns out that this set is countable because I can view it as union of several countable sets. Okay, so let S1 denotes the real numbers consisting of only ones, where you don't have anything before the decimal point, and after the decimal point you list down all the numbers starting with the real number where you have a recurring ones. That means you have a series of infinite ones and occurring again and again, followed by the real number 0.1, followed by the real number 0.11, followed by the real number 0.11, and so on. Remember, 0.1 is not same as the real number where 1 is recurring. Okay, 0.1, you don't have anything after the first one here, but 0.1 with a recurring one denotes this real number, which is clearly different from 0.1. Okay. So that's though these are the elements in my set S1, and I have a valid listing here. Then in S2, what I do is I will list down all the real numbers whose decimal representation has only ones, and where before the decimal point I have only one digit. Okay, so so these are the elements in the set S2. In S3, what I am going to do is I will list down all the decimal numbers whose all the real numbers whose decimal representation consists of only ones, and where before the decimal point I have two ones. Okay, so you can imagine that when I am considering the set Si, I will be focusing on all the real numbers whose decimal representation has ones, provided there are I minus 1 number of occurrences of 1 before the decimal point. Okay, and after the decimal point I will give preference first to the recurring occurrence of 1, then 0 occurrence of 1, and 1 occurrence of 1, and 2 occurrence of 1, and 3 occurrence of 1, and so on. And each of this listing is a valid listing, and if I take the union of all these sets S1, S2, S3, that will give me the bigger set S. So that means now I now have a valid listing here, and bigger set S is the union of several countable sets, and hence the bigger set S will be countably infinite. Okay, so that brings me to the end of this tutorial. Thank you.